Hey everyone, and welcome to this explainer. Today, we're diving into something that is literally everywhere but completely invisible. We're going to unpack the hidden technology that powers modern automation, robotics, and all the measurement tools around us. We rely on machines to monitor our world, right? But there's this massive, hidden step right at the boundary between the physical and the electronic. So today we are exploring exactly why our advanced instrumentation systems absolutely require devices called electrical transducers just to function.
Think about this for a second. How does a tiny piece of silicon actually know that it's hot? Or take your smartphone. It's basically just a block of glass and microchips, right? So how does it know it's being tilted when you flip the screen? I mean, a computer doesn't have skin to feel heat, and it definitely doesn't have an inner ear for balance. There is a total disconnect between the messy, physical environment and the electronic brain of our devices.
To really wrap our heads around this, we have to look at it like a massive language barrier. It's like two completely different worlds trying to talk. On one side, you've got the physical world, which speaks in variables like temperature, pressure, flow rate, and pH. But on the other side, the digital world of microprocessors. And that world only understands one language, electrons. We're talking voltage, current, and frequency. It is a fundamental language barrier. And to bridge it, we desperately need a translator.
Okay, let's look at our roadmap for bridging these two worlds. First, we'll cover the language barrier, then enter the transducer, sensor versus transducer, how transduction actually works, and finally, the real-world translators. Let's jump in. Starting off with Section 1, the language barrier. So you might be thinking, if we want to measure something, why can't we just, look at it? Well, in modern instrumentation, we are very often dealing with hostile, completely inaccessible environments. I mean, humans cannot safely just stick a thermometer into a nuclear reactor core to check the temp, right? Plus, you obviously can't visually measure the gas pressure or the liquid level hidden inside a solid steel tank. And here's the real kicker. In automated closed-loop systems, the system needs constant readable feedback to even function. Simply put, you cannot control what you cannot measure. So since we can't measure these things directly with our own senses, we absolutely have to have a device to step in, grab that physical data, and convert it into a safe electronic format that a computer can rapidly process.
Which brings us to Section 2, enter the transducer.
So what exactly is it? Well, by definition, a transducer is a device that converts energy from one form into another. Now, in the specific context of instrumentation, it takes a non-electrical physical quantity, say mechanical force or heat, and transforms it into a readable, proportional electrical signal. It is, essentially, the ultimate translator. It takes all that raw physical energy and perfectly converts it into the exact language of voltages and currents that our data systems actually understand. Now, looking at a typical data acquisition setup, you can see how the sensor really acts as the front line. It sits exactly at the boundary, grabbing environmental data from the physical object, and then it passes it through an interface straight into things like a multiplexer and an analog to digital converter. Without that crucial bridge in the middle, the computer on the right would be completely 100% blind to the physical object on the left. Moving right along to Section 3, sensor versus transducer. Now, a lot of folks, even in engineering, tend to use these two terms interchangeably, but there is a major difference. A sensor simply detects physical changes. It's really just the sensing element itself. Because of that, it's relatively simple. It's the least complicated part, and crucially, it doesn't necessarily convert energy. A transducer, on the other hand, actually converts energy forms. It's the whole package, the sensing element plus a signal conditioning unit. And because it has to physically transform the energy and prep the electrical signal, a transducer is much more complicated and much more expensive. The big takeaway here is that every transducer contains a sensor, but a sensor on its own, it is not a complete transducer. To make this super clear, think about this anatomical analogy. A sensor is basically like the human eye. The eye perceives light and senses the environment, right? But a transducer is the eye plus the optic nerve. It doesn't just perceive the stimulus, it processes that energy, converts it, and delivers the readable message straight to the brain, or in the case of our instrumentation systems, the computer. All right, Section 4, how transduction actually works. Let's peek under the hood and see how this builds step by step. The process of transduction basically involves three main steps. Step 1, the sensing element detects the physical change in the environment, like a sudden shift in pressure. Step 2, the transduction element converts that physical energy form into an electrical form. But it doesn't just stop there, and this is important. Step 3 is absolutely vital. The device has to condition and strengthen that electrical signal so the computer can actually use it. So you might be wondering, why is that third step, signal conditioning, so necessary? Like, why can't we just take the raw electrical conversion and run with it? Well, raw physical data translated into electricity usually gives us incredibly weak signals. Sometimes we're talking just a few millivolts. Not to mention, real-world industrial environments are incredibly messy. They introduce a ton of stray electromagnetic interference and electrical noise that has to be filtered out. And finally, computer inputs require highly specific voltage or current formats to be read accurately at all. So signal conditioning takes that raw, weak, noisy pulse and amplifies, filters, and formats it into a robust, readable signal.
And finally, Section 5, the real-world translators.
This really illustrates how these devices are just hidden in plain sight everywhere around us. Take the accelerometers in your car. They measure rapid mechanical deceleration and instantly convert that into an electrical signal to deploy your airbags in a fraction of a second. Or think about medical ultrasound machines. They use piezoelectric transducers to convert electrical pulses into acoustic sound waves. And then they transduce the echoing sound waves back into electrical signals to create an image of the inside of the body. Even the antennas on your smartphone are transducers. They convert invisible electromagnetic waves in the air into electrical currents. And the thermistors in your home's HVAC system, they constantly change their electrical resistance based on the physical temperature of the room just to tell your AC when to kick on. It's literally everywhere.
So, as we've seen, transducers are quite literally the senses of the modern world. They are the essential bridge allowing microprocessors to interact with reality. But it leaves us with a pretty fascinating, maybe even slightly unsettling thought to close on. As these physical to digital translations become entirely seamless and completely invisible to us, what happens to our own understanding of the physical world when the machines around us can feel it, measure it, and react to it better than we can? Anyway, thank you so much for joining me for this explainer. I really hope this sparked your curiosity, and I highly encourage you to keep exploring the invisible instrumentation systems all around you.